first time streaming on YouTube. I've never streamed on YouTube before. I just want to try it out. And yeah, let me get to the bathroom real quick and I'll actually start the stream. But before I actually do that, I actually want to do something. So I want to upload an image. Select the file. Select coding. Stream. I have like a to-do list. Here are things I want to complete. For the most part. So it's gonna be right here. I don't know if that's CBOLN. Let's see. Yeah, that's valid. So yeah, it's just a little to-do list for all the stuff that I want to do when it comes to my summer. And like it's developing, deeper skill set when it comes to computer science. Yeah, so that's when I'll be spending my senior summer year, going to fall, making sure that I have all this stuff like hammered down, so I'm prepared for like any job interviews or any just bolstering myself as a better jobs prospect. So I will be right back. I'm gonna do something real quick, and I'll be right back. let's get to work. So we are going to start off with embodies. It's creating a little simulation benchmarking program. We're benchmarking embody solution. So we have like 3 different programs. So like SIMD. So we have the non-SIMD version. So regular like way that you program it with AOS. We have structures. You have the non-SIMD, SOA, structures of arrays and SIMDs, with AOS and SOAs. So like these aren't like if you're using SIMD and you're not taking advantage of like all the lanes, then it's very useless and there will be like bottlenecks, right? So what I want to do this stream is actually do like actual do true SIMD, right? We actually like try our best to develop a program where it takes advantage of SIMD, because like we're not using it right now. We're doing like we're on no optimization, so it's basically up to us to develop like the optimizations, and then we're not relying on the compiler to do that for us. So when we're doing stuff on ourselves, because like right now I'm writing this simply myself, so right here I'm writing this simply, but there's probably like the compiler probably will generate a lot more efficient way of doing this if I have it on a different optimization level. However, I don't want to rely on a compiler at this point. I want to be able to write the code myself and like kind of bang my head on it until I like finally get it right. And my job is to just make it faster than what it is currently, and it's not that fast. I've already been doing like the benchmarks, getting the numbers for it's like the assembly version or the SIMD version. Like both SIMD versions are pretty slow. The SOA version is slow, but that's mostly because once again we're on no optimization, so like the compiler's not taking advantage of the fact that our not taking advantage of the fact that like we can do a lot of this. We can vectorize most of these problems because they're in arrays, but we are going to write that ourselves in this program. So what I want to do is, I already have code for like the addition. So if I go here, I already have the SOA code for addition, and what you can do is you can do like large allocations, right? So what I'm gonna do is this. Or we can keep. So we can do keep the SOA because it's only SOA anyways. But we can just do defined true SIMD. So I created like basically a naive version of SIMD, and then true SIMD. So I know I'm very aware that this is probably like the most scuffed way of doing this. So we're gonna do this, I'm gonna do this, and then we're gonna do back to so basically this is just throwing all to positions, right? So we can do where all the data for the embodied now we have to do. So we can low-key start. We can do like, L if defined true SIMD. We do sim bodies that. Or we can do okay, so I kind of already know what I want to do. Let me see if I can do it right here. Because we don't have like the thing is in this situation we don't need to go through every single value. This out. This first. Let's see. Interesting. Get this up here. Nice of it. Those people able to determined. That's fine. We can do. Well, first, we can't arena allocate, right? So we have to do something else. We have to align Alec. Yeah, we have to align Moloch and give a specific alignment, which in this case we're going to use 16 as our alignment. So I'm going to have it up here so I can just use that, and that's going to basically allow us to. So there's a reason why we need to align it. Let me search it up so I don't just say BS. But there is. Why do you need to align memory when dealing with SIMD? You align memory for SIMD to ensure the CPU can load and store data in a single efficient operation. If data is online, the processor may perform multiple partial loads and immerse them together, which creates a massive performance bottleneck. I think that's so it definitely has to do with mapping to system cache lines and like making sure that like we're putting the data and it's always going to be in the cache line that we're expecting it to, rather than like it being fragmented. Not fragmented, but like it's not going to be in that same cache line, so we have to wait, and that causes like cache miss, and that is just adding latency to our program that's unneeded, which may or may not ruin the performance benefits to SIMD. It might add more cost to it. So that's the reason why you need to align your memory properly. And I think memory alignment is based off operating system, like your CPU, off a 64-bit CPU, and let's see. CPU. Yes. So right now, I'm not doing anything that's like, I'm only doing SSE, so I only need 16. But let's say I want to do AVX, use 32-bit, AVX 512, 64-bit, which later I might start doing the AVX and AVX 512. This allocates memory regardless. Oh my god, bro, I'm really in like macro. If this is defined as singular. So that means it's true someday. We can do sim bodies positions. We have aligned malloc here. It's just part of a library that I made, so we can do splits. We have like a library. And then we have lines. Is it here? Like, where is that function? Is or is that a different library? Where is that? Oh, interesting. What happened in this library? Interesting. Okay. Different base. So we have to switch this to base. Base. Line malloc. So it takes in the pointer. It takes the amount that we're allocating. And I think that's it. So we have to do aligned to malloc, sim bodies. right now, like we don't. I'm not really doing anything on the initialization stuff where I like. Where I'm worried that like, I could do Cindy with this, right? But it's like I don't think it's that much of an issue if I simply just work with the values. What a Dylan is back to F. Just float pointers, right? That's basically what all this is. They're just float pointers to store the data. So what I'm going to do is I don't need. I can just do bodies, position, X. I can get away with that. It's not really like an issue. And then I don't want to confuse myself. I'm actually going to let's see the positions. Let's see the certain positions. Like I'm pretty sure I can still render this. Right, so I can go down here and just render the positions that I've set. They're not doing anything with this, is what I'm trying to say. Like, we're not going to update, just going to print the initial position, so I can just do. I was going to stay as away. So that's the issue. The position is not what's an array or like when it's the object. It's just things. I should expect, create should be anything. You're not running really. In a position. It seems good. So we go back to main. Let's go back to main and start writing some code. I want to do. Scratch this entire loop. We don't need to do this loop anymore, right? Because we're gonna do additions based off of big values, right? So we already have a vectorized add where we have this is what it looks like, right? So probably need to look up this again because I ran it and I didn't comment it out, so that's on me. So what we're doing is, okay, remember that our vectors store pointers, right? So these we're just sending a pointer, so we're storing a pointer of the values that we have stored in that pointer. There's the memory location, and that memory location holds the values of what we're representing in the struct. So in this case, it's positions, right? And we want to represent positions. So we have X positions can be stored in one, register, and we can have whatever that we're adding by stored in the X in another register. We do that for all the things that we're adding. So when we're adding, how we add vectors, like a.x plus b.x, comma, or b.y, a.y plus b.y, and that results in the final vector. We do that same thing, but we do it in one sweep rather than iterating. We're iterating through the values, because before you would have to iterate through the values to add them. However, you can do this in just one go, and that's a lot easier. Not easier, but it's a lot faster to do. Probably has, I would say, there is the caveat of there's gonna be a lot. I need to measure it, but I'm pretty sure the memory usage should be more. But the benefit is that the performance should be better because you're doing it in one go instead of doing it in multiple different iterations. You looked at in our naive code. In our naive code, we're doing it for every value until we hit the limit, which is the sync count, right? So yeah, so we don't need to do this. So we can do if defined see if we can do making sure we can do if so find true sending. This is the actual computing of the position. attracts every other particle, force directly proportional to the particle of their masses and inversely proportional to the square of the distance between their centers. It explains how gravity governs everything from falling apples to planetary orbits. And this is what we're putting in code basically, right? So we get the masses of the two objects, the gravitational force constant, and then the distance between the two objects squared. Right, so through our code, we can like find it like where your but yeah, I mean, I don't want to spend too much time on the part, but that's what we're doing when it comes to that. Right now, let's do. I want to be able to add. So I want to do it this way, right? Which way? Let's put on this so I can lock in. I'm going to add a position. Let's first get the scaling of two values. Right. I had a difficulty. I actually had a difficulty doing scaling yesterday. So let's start off with scaling, right? And we're adding the scaled value with the velocity, and we add that result with the position. It actually gives us the final position of our what should I call it? Of our end body. Okay. Let's go to yes, let's go to scaling function, right? So we're just taking all the values, scale. actually going to make this a winner because it's easy to work with. what's in this code? So I want to the scale right here, right? Okay, similar to how I did it here, right? When I do the scale, broadcast it. Yeah, so similar to what I did there, no? I'm pretty sure. So when we move APS, right, so when we move the scale, it's only moving to one lane of the register. When we broadcast it, I'm pretty sure it goes into other lanes. So this allows us to like put the scaler into all the lanes. Let's get to the first value in our register and like take all the different lanes. And this allows us to multiply. Now we can multiply those values. And so we do PS. And we can do this. We don't want to move the entire thing. We want to move to a certain point. So if it's move quad, in this case, it might be move APS again. So move APS. Is it 1? Is it 1, 2? first try. I didn't even read the thing or like any documentation. But even I got it first try, it's simply so weird. Like this probably was the most inefficient way of doing this. So probably should read it to get a better understanding. I can do is I just do sim position actually that's not just do this might segment fault. And we can do some position. Restoring the result in positions. Undefined operand. Undefined name operand. I don't get that here. Let's see. That's good. GDB. had the bucket of squirt dwarfs, so I can like just plug this back in and stuff to it that way. Let's see if it actually works, because this point, right? So we're at this broadcasting. We should this print here, so 0.5. that's the correct value, right? That's what we're expecting. Back to like the resulting register. And then, am I allowed to just do print, like do the same print, but I can just do array instead? How does that work? Like, how do I represent? Data registers as a vector of floating point values. Like things I can cast. That's fair. Okay, got it. Values. Yeah, this register. XMM1. No. XMM1 is the result of that result register for the initial calculation. Now we're about to move the value that we received from the parameters RDX into XMM1. So let's set this. We do RDX. Right? RDX stores all the values that we have. And I think it's like we can't go over 256 because that's the like. If we are doing this correctly, anything past 256 it's not valid. I think you represent anything past it. Yeah, so I do NI, and then I do XM1. This is a invalid cast. Let's see if I can do. That's an invalid cast? Okay, so since we moved the values, we should have the same values that we had in RDX and XM. This is what we are trying to. But it's not working because this is a reference and now seeing podcast. I don't know. Yes. Okay. So if I do 256. So remember, oh, that did not work for some reason. Interesting. Wait, you can only subtract 4. Interesting. So we only have the 4 here. It's kind of odd. Why can't I see the registers like any value in the register? Registers lane, I don't know. Reading or assembly. Now we're going to multiply the values in XM1 by the scale that we have already set. So we set it right here, and 0.5. And by multiplied by 0.5 is half that value. Now if I go to XM1 again, the values are halved. And XM1 stores the Y positions, or at this point it stores the Y positions. RDX stores the right positions. R8 stores the X positions. Or wait, no, it doesn't. It stores the X positions of the resulting vector. But the X, it stores R8 of the resulting vector of the X, like the resulting vector's X positions. So all the X positions that we have for each n body is stored in R8, and all the Y positions of each n body is stored in R9. Sorry. So now since we're here, so R9 should just be garbage values as of right now, because we haven't done anything to it. So we do R9. Like, it's not going to show anything. Or, see if we can go here. R9. Or maybe, I don't know. I know why. I really don't know why, honestly. If I do this, we should have the values that we want, right? So we have the same values. X1, R9. I don't know why it was already pre-stored here. Wait, why? Am I reading this incorrectly? Nah, I think that's just GDP. Well, yeah. So, based off of what I've seen here, I'm pretty sure my values are correct. I can just run it and I'll just see. Wait, sorry. No, it should just work. So we fixed our scale. To get a scale, we need to now subtract. This is the same. I'm gonna see what I'm adding. No, that's gonna be this. I might just end like 45 minutes because I am getting tired and a little bit hungry. Yeah, let's try to finish it right now though. Subtracting shouldn't be that hard. I'm pretty sure you can get away just doing this, right? We can just do sub. Except we want to switch, probably switch. Like, do I have it? Big value. Basically almost done. I wish I get the magnitude. Um, that's correct. Nice. We can now start repeating the velocity. I mean the acceleration. Slow gravitational pull is. It's not the final ascending. And now just do. Let's do. So this allows us to get the positions. So we do need a loop, right? We do need two loop for this problem. How will we go about it? I think I'm done for today. I'm not gonna lie. I'm kind of fried. And I know like the next part of this is probably gonna get the bulk of the work. I want to reset because I'm like guys, whoever attended the stream. Hope you guys have a good day.